Alright, so here I'm trying to solve this problem called network delay time. Let's quickly have a read. We are given a network of n nodes labeled from 1 to n. Okay. We are also given times, a list of travel times as directed edges. So it's a directed edge from one node to another. So U, V is the source and destination, and W is the weight of that edge. So it's a sort of a weighted graph where U is the source node, V is the target node, W is the time it takes for the signal to travel from source to target. We will send a signal from a given node k. So some one of the random nodes will be chosen and that will be considered as the source. Return the minimum time it takes for all the n nodes to receive the signal. Okay. If it is impossible for all n nodes to receive a signal, return -1. So for example, in this case, this is a graph and k is chosen as 2. So that means this is the node and okay, the minimum distance, the longest is taking is there. So 2 is the answer. So so basically we have to find the shortest distance from a source to all the given destination nodes. This is the typical Dijkstra's algorithm. So now, it's essentially we just take the source and follow the Dijkstra's algorithm to find the shortest weighted path from that node to all the other nodes. So let's quickly talk about what that algorithm looks like, right? So in Dijkstra's algorithm, we basically keep two sets, right? One is a set which has a uh, already min distance and others and the other, right? So initially what we'll have is, oh come on, all the only the source node will be kept here and in the min distance set, and all the others will be kept in the other all others, right? And now what we will do is from the source, we will initialize some distance to all the target nodes. And let's say we'll initialize it to some very high value. And now uh, the first thing that we will do is this. Uh, from the source, whoever is, for example, in this case, 2 is the source. So whoever is its direct adjacent neighbor, in this case, these 1 and 3, we will update their distances. So right now, let's say initialize to distance to infinity, and then we will take source and the other guy, in which case either of the two, whichever is smaller, that we'll take. So in this case, we'll take 1. And so, okay, so in this case, let's say 2 as the source. So what we'll do is, let's say initially everything is kept here. So 1, 2, 3, and 4, everything is kept here. And we'll also maintain something called as uh, okay, distance 1, distance to 2, distance to 3, and distance to 4. And now what we'll do is this, if distance to 1 will take as infinity, distance to 2 will take as 0, distance to 3 will take as infinity, distance to 4 will take as infinity, right? Because 2 is a source, we know this distance to 2 is 0, right? And now these are our sets. Now what we'll do is we'll take the smallest guy, whichever is the smallest guy. So 2 is the smallest, distance to 2 is the smallest guy. So we'll move 2 to this set and everything else will remain here. So now we remain 1, 3, and 4. What they, what other thing that we'll do is we'll update the distance of this adjacent neighbor. So one now distance from 2 to 1 is just 1, right? So we'll change this from infinity to 1. Similarly for 3 also, we'll change it to 1, right? And then whichever is the smallest, so 1 or 3, either of the two we can take. So now we'll take 2 and 3, let's say, right? And so here we are left with 1 and 4, and 3, whoever is 3 is neighbor. So 3 is a neighbor is 4. So we'll update the length of 4. So how will we update it to? So uh, distance of 4 equals to uh, min of distance to 4 comma distance to 3 plus edge from 3 to 4, right? So here you see distance to 3 is 1 and the edge from 3 to 4 is also 1. So 1 plus 1, 2. So in this case, distance to 4 will then change to 2. And now we'll take 1 here. 1 doesn't have any updates to make, so only left with 4. And then you take 4 out as well here, and so you 1, 2, 3, 4. So and these will be the shortest distances from. So that's the sort of the idea. This is the main equation to check. Like you pick out the guy with the smallest distance, and then you update its neighbors using this formula that whatever distance I know to the node, either that or the distance I know to the smallest node plus the edge from that node to this node, right? So that is sort of the formula. Now, uh, every point we want to get to know the smallest distance, right? So this is sort of like the priority queue concept, right? The other thing is we have to notice is that we are also updating the distances, right? So in the priority queue, then we also need the capability to in the priority queue, we also need the capability to update the priority sort of. So either we can try and modify the priority queue to do that, or we can take a slightly different approach where whenever the priority changes, we'll just insert that key with the new priority as well into the um node, and we'll always take the smallest priority of a given node. So what I mean by that is, let's say initially 4 is added with a distance 5, just as an example, and let's say later on distance to 4 gets updated, and the distance to 4 initially was 5, and now distance to 4 gets updated to 3. So ideally we have to change the priority of the 4 to 3 here in the priority queue, but and we have to modify the priority queue data so to do that. Or we could do is we can insert another node 4, 3 in the priority queue like that, and then uh, we will not consider, we'll only consider for a specific node, we'll only consider its smallest value, right? If and then we basically when we are dequeuing from the priority queue, if you have already dequeued 4 once, then we will never dequeue 4 again. Or when we dequeue 4 again, we'll ignore that bit. So that is a workaround to do sort of the thing around when we update in the priority. So that's the thing. I know I just went about it in a slight fast manner, but when we code, I guess it will be a little bit more clear. So let's start with the code, right? So, okay, so what is given to us? We are given the times, we are given number of nodes, and we are given the source k. How are the times given? So times are given as source node, destination node, and their weight. So let's first do this. Let's first define something called as an edge, right? So an edge has what? Edge has a source, edge has a destination, and edge has a let's call it weight or what? Let's call it weight, right? Just for simplicity. And now let's define a constructor for it. So right, so this is excuse me. So this is what we define as the edge. Now we have to create a graph, right? So a graph has a sort of an adjacency list. So and what will be our adjacency list? So one of the things to note here is we are given a network of n nodes labeled from 1 to n. So we want to define an adjacency list. Adjacency list firstly has to be indexed on the nodes. So we could either create an array or a map or whatever, but let's for simplicity, let's create an array. So we get a list of what? So we get a list of maybe another list of edges, right? A list of edges, and this is what we are calling is the adjacency list equals to now. Another thing to note here is it's from 1 to n. So for simplicity, we'll just create from 0 to n and just ignore the index 0. So for I equals to 0, I equals n equals to n, I equals plus. Uh, so we created an empty list, and within for each of these, we are creating another empty list, right? So new And now we go through this times array. So we're going through each row of the times array, and what we know is so source is times of I 0, and destination is times of I 1, and weight is times I 2. So this is a new edge that we're going to create, and we're going to create this new edge in the adjacency list of source. We are going to add a new edge, and the edge is defined by source, destination, and weight. So that makes sense. Because edges are certain adjacency list of a source, we probably don't need a source in the edge, but okay, it's fine. So this is how we define our adjacency list. Now, let's define the min distances, right? So we take an array, we call it min distance 2, and an int array of size. Again, we'll take n plus 1, and let's take 0, who cares? I plus n equal to plus. I guess other thing we could do is this. There is a shorter way, right, in Java, and I mean it's language specific, but fine. It is we can do arrays dot fill, and we can give it some max value, but the source will keep it as the smallest. So the source, which is k, so we'll do min distance to of k as 0. So this is our min distance to set. Now we want to create a priority queue, right? So, and in this priority queue, what we will keep, it's interesting, but so we'll keep uh, so let's define another sort of class. Who cares, right? So let's define another class called distance to node, or just call distance node, right? Or distance info, min distance, whatever. Okay, so distance info, and these two things, int destination and int distance is what we have, and let's do public edge int destination node int distance, and source equals to source. Sorry, I was copying from there, but DST and DIST, huh? Interesting. Uh, and now what we'll do is so we'll create a priority queue of distance info, priority queue equals to new priority queue of type, and we can say comparator dot comparing okay. I think this was a newer syntax that I had read about. I'm gonna have to search about it again. So comparator dot comparing. Okay, let's quickly have a read. Hmm. Okay, string int name age salary or testing data implies this. Comparator comparing key selector. Come on, hey, right. Okay. Yes, so it says is get name, but is the name like hmm. Okay, we'll try it and we'll see if it works. So we'll do get list, right? And so that's that. So we'll find the priority queue here. And now what do we want? So in the priority queue, we'll initialize it with the source, I guess. So priority queue.add, um, a new distance info with the node as k and the distance is 0, right? And then we'll do while priority queue is not empty, we take the item out of the priority queue. So you remove item from the priority queue and then you check what. So one thing you check is if so okay, so int node equals to if min distance 2, right? This is the array, yeah, min distance 2 node. If this is already equal to or greater than the distance that I'm seeing, that no, if it is less than or equal to, right? Then it's not. Then you have that means then you have already considered. Okay. No. So if this is greater than this, then only it's a problem, right? Sorry, less than, yeah. Yeah, if this is already less than this, then you've already considered a smaller distance than this. You don't need to worry about this at all. So just continue. This is the case of that ignoring bit. If the node is already considered the smallest value. But other than this, all you will do is so you remove this node, which is fine. Now you have to go through all its neighbors. So for each edge in the adjacency list of node, sorry, of the adjacency list of this node, we gotta do this edge weight equals to so if min distance 2 of this destination, if it's greater than min distance to the node plus this edge weight, then you update the min distance 2 of destination to min distance 2 of node plus this edge weight. And yeah, you keep doing that till your is priority queue is empty. And then at the end, what you do is you have to find the max of shortest, right? Equals to If there is still some node which is at max value, right, then you would return -1. Otherwise, you would return whatever is the max shortest. That's our solution. Let's run code. Obviously, there will be some compilation errors. We'll try and fix that. Okay, so in this center, method declaration, public, yeah, we copied from edge. So, okay, so yeah, it did not understand this. Invalid method reference. I really want to be able to use this, so I'm gonna have a read again here. So I'm gonna use proper Java docs. Comparator dot comparing. Yeah. So this is comparator comparing. You define a function and you define a key extractor. Yeah, I need an example for this. See here, comparator comparing person get last name. So what I want to know is this is get last name of a getter defined or what? So okay, let's see this way. Yeah, okay, they have defined a function like this. So you do define a getter and setter, huh? Let's try and define a getter here and see if that works. So list info. And if you run code again, if it causes an issue. Uh, okay, but so this is fine. So you define you need a function there. Fine. Line number 62. When distance to of more than the I, a bad operand for binary operator less than. Right, it's just. And we got the wrong answer. Okay, so output is -1 expected is 2. And why did that happen? The thing that we missed, right? So when we update the min distance, we also need to update our priority queue over here. And so what we need to do is so you add to the priority queue new dist info dst and min distance to dst, right? And it works. Let's run for another example and submit. Alrighty, so that's it. Learn a little bit about the time complexity maybe. So let's go back to this, right? So what's happening here in terms of time complexity? So essentially we have a priority queue, and we know from the priority queue the insert delete is um, log n, right? So, and so question is then how many insert delete operations are happening? So let's look at the code. While priority key is not empty, is we we keep on removing one edge. So how many maximum number of entities in the priority queue could be? Each edge, right? Because it could be that for every edge you may be doing this. So for every edge, so it's if the number of edges is e, then it's e. So the overall time velocity of the finding min distance is e log e, and later on we are also doing this for loop, and this for loop is running for number of nodes. So the overall it becomes v plus e log e. All right, so that's the another things. If you look at the Dijkstra algorithm, typically people would say the time complexity is e log v, and I think they claim it's because well, log of e is pretty much similar to log of v because um, from a logarithmic perspective, because at worst, the e can be v square, and so uh, log of v square would be 2 log v. So, in terms of um, the asymptomatic, if you want to try to determine more in terms of v, so you can either say it's v plus e log e, or you can even say it's v plus e log e. All right, so that's that.